Welcome to the video on routing protocol. Before we go into the details of the routing protocol, we must understand the difference between routing and flooding. So flooding means what? Let's say packet, we want to send the packet from, let's say, A to B. In that case, A will forward it to router R1, and then router R1 will send it to all the other routers which are whatever are connected to it. And when it reaches to R2, R2 will send it further, R3 will send it further. So the point is, B may receive the packet from R1, R2, and some other through that route, and maybe even from R1, R3 through that route. So what are the advantages of flooding is like there is no routing table which is required to be there with the routers. And what is going to happen is, it is always going to have the shortest path. Right, so shortest path is guaranteed with the flooding. So B may get the best solution, the best path solution, and will the packet will reach through that path, right? And then there is the reliability which is going to get increased when there is flooding. Why? Because now if the router R1, R2 path is closed, then R1, R3 path may be still working, and so reliability of the packet reaching to the destination is always going to be very high. So where do we use this type of flooding mechanism? Is normally we don't use it in the internet, but no, in the military applications, it is finding its place very heavily, right? And if you see the advantages, whatever the advantages of the flooding are there, on the other side, it becomes the disadvantage of the routing. So when we say routing, so routing tables are required to be there, and in the routing tables would be required, as well as the shortest path is not guaranteed and reliability is low, right? So when we talk of the routing, the advantages part, then what is going to happen is that will be no duplicate packets. So duplication is not going to be there, and there will always be less traffic, right? So when we say this, this advantages of routing becomes the disadvantages of the flooding. So there could be a possibility of duplicate packets, because we know that when the packet from A is sent to B, say R1 to R2 path, R1 to R3, R1 to R4. So there is going to be duplication of packets, right? And resulting into what? Resulting into heavy traffic. So these are some of the advantages and disadvantages of routing and flooding mechanism. So before we go into the routing algorithms, we must understand what is the actual meaning of routing algorithm, right? So routing basically algorithm means what? The process of preparing the routing table is known as routing, and the algorithm that is used to prepare the routing table is known as the routing algorithm. So there are two types of routing algorithms. One is static routing algorithms, and another is dynamic routing algorithm. In the static routing algorithm, if the routing algorithms, what is going to happen is that routing algorithms are prepared manually and uploaded offline, right? And there is no such entity as such who can keep track or record all the routers in the world, right? Because every day one or more router will go off or on. So this situation may result into various other problems. So there is no central as such agency or organization which controls this. And so what is happening is, for every change, manual updation is required over and over again, right? So depending on the traffic and the topology, they don't as such they don't change, but that is the problem with this, right? So depending on this, the traffic and the topology, when they change, there will be a change which is required to be done in the table, and it has to be done manually. So these methods are actually not used in the internet. So what is used in the internet as of now is the dynamic routing algorithms. So everything is done by the routers automatically in the dynamic routing, and there is no manual intervention. So depending on the changes in the topology and the traffic, the routing tables will change dynamically. So these algorithms are generally used in the internet, and the most popular algorithms are distance vector routing and the link state routing, right? So we will see the distance vector routing algorithm. we short normally know it is referred to as DVR and LSR for link state routing. So in the case of DVR, distance vector routing, it has been in use. It has been used since the invention of the routers, and since 1980s, it is very popular. Uh, we are worried about sending a packet from router to router through shortest path, right? So if it could be done efficiently, then anyway networks are directly connected to one hop routers, right? So I am pulling out all the networks in between, and which are there in between, and just putting all only one router to another router. So in fact, if you see A and D, so there is router to router. Actually, there will be some network in between. Likewise, no, all the A, B, B, C, C, D, D, B, all such links, no, will have the intermediate networks which are there, and then the other side there will be the router which will be there. So I'm just removing those networks and just connecting the next router to it. So one hop routers, right? So this first step in the DVR, distance vector routing algorithm, is every router will construct its own local routing table. So step one is to construct the local routing table, and what will be there in every routing table, it will contain basically three things. One is the destination, the other is the distance to that destination, and the next hop, right? So in that way, in this way, no, the local routing tables will be created for every router. So let us create the routing table for, let's say, for everyone. Let's say for B initially, what will be the routing table looking like? So for the routing table of B would be like a distance from from B to A. Distance from B to A is 2, right? So destination is A, and distance to that is 2, and the next stop is A. Likewise, from B to B, it is 0, and the next stop is B, right? So likewise, what will happen is from distance from B to C is 3, and the next hop is C, and distance from B to D is 7. Distance from B to D is 7, and next hop is D, right? So in DVR, every node knows only about its neighbor, right? And it will never know about the node which is not its neighbor, right? So only the nearest neighbor information is present with the router, and the so prepared from this table would be prepared based upon the local knowledge, right? And using what about using what it knows from the neighbor, so it is going to prepare the table. The second rule now is likewise, no, all the routers will be preparing the table. Now the second rule is every node knows how many routers are there in total. So this information is known to every router, that how many total number of routers are there inside the system, inside the total network, right? So using that only, no, it is going to prepare this tables in an iterative manner. So in the next stage is let's say routing table at A would be what? So using the same diagram, routing table of A would be what? A to A is 0, and then A to B is with 2 distance. So distance of 2, and next hop is B. Then A to C is not defined, so that's why infinity and dash. So next hop is not known. Are you getting it? So A to C, there is no path, direct path, right? So it is infinity and dash, right? So next stop is not known. A to D, there is one edge which is there, which is saying that 1, and with the distance 1, and D is the destination. So likewise, a routing table for C, if you see, then the routing table of C would be what? C to A. C to A is infinity, is not defined, and that's why next stop is dash. So C to B, there is a path which is of length distance 3, and the next stop is B. C to C is 0, right? And the next stop itself is the same one. And C to D, if you see, there is 11 distance, and next stop is D. Likewise, routing table for D is prepared. And what will be the routing table for D? So D to A, if you see, it is 1, and next stop is A. D to B is 7, and next stop is B. D to C is 11, next stop is C, and D to D is 0. So in the first step, what we have done is, in the every router is going to prepare the local routing table using the knowledge about its neighbor, right? And in the second step, what is going to happen is like every router will take its distance vector. So entire vector, no, that 1, 7, 11, 0, 0 to infinity 1, infinity 3, 0, 11. These are all the distance vector, right? So the middle part in the table is this distance vector. Is nothing but the area of distances, right? So this area of distances, and they will then exchange this them with their neighbors. So second step would be to exchange the vectors. And for example, C will send it to B as well as D, right? So C will send it to B as well as D. At B, it will take its distance vector and send it to C, A, and D, right? So like that, no, distance vectors are exchanged. So every node is going to get a distance vector from all its neighbor. For example, A is going to get distance vector from D as well as B. C is going to get distance vector from D and B. So everyone will get distance vector from everyone. This is what I want to say. And based upon that, no, what we will have is we will have the DVR. We will have the DVR for at A. DVR at A, and we'll get the distance vector from B and D. At B, distance vector from A, C, and D. At C, we'll have the distance vector from B and D. So all the neighbors, right? And at D, distance vector from A, B, and C. So everyone is going to get distance vector from every neighbors in parallel. Understand? So everything is happening in parallel, and they are actually meaning of this is means what, that it is going to make use of full duplex channel. So distance vectors can go in both the directions and in parallel, right? So now at every node, using this distance vector, the new routing table will be created, right? So at every node, it is going to happen, right? But let's say at node A. So node A, what is going to happen here is then node A, distance vector will be received from B and D. So from B, it is receiving 2037, and from D, it is having 1, 7, 11, and 0. So a new routing table is supposed to be computed, right? So what is the meaning of this? How it is going to compute is, let's say A to B, right? So from A to B, what is the minimum distance which is going to be there is C. So there is a path from A to D and then D to B, right? So A to D, there is a direct path, and there is also a direct path between from A to B, right? So when we want to find out the routing table, the new value of that, no, then we need to see which one is the minimum path, and direct path and including the, I mean direct edge and including the path which is having more than one edge. So A to D and then D to B is also possible. So we just see the bottom one. I'm talking of the bottom equation, right? The equation which is written below the table. So A to B and then B to B, right? So what is that? Is 2 plus 0, that is 2, and 1 plus 7 is 8. So minimum of this is 2, right? So for path from A to B would be what? 2. Distance is 2, and the through which hop B, right? A to A is always 0, so that is already kept in the first row. B is 2B. Then similarly we calculate it for C. So A to C path, no, if you see the table, if you see the diagram, then there is a path from A to D, right? A to D and D to C, right? So A to D and D to C, so that is 1 plus 11. And then there is a path from A to B and B to C, so which is of 2 plus 3. So what is the minimum of this? 2 plus 3 is 5, and 1 plus 11 is 12. So minimum is 5. So that's why in the third row we have written C, 5, and through which next stop is B, right? So 2 plus 3. So in that way. So next, likely, no, we similarly we calculate it for A to D. So A to D, we know that no, there is a direct path from A to D with a distance of 1, and then plus D to D, that is just for the formality. And then there is a path from A to B, then B to C, and then C to D. But see, there is that path, no, B to D is also there, which is of 7. Instead of going for 11 plus 3 plus 2, there is a path from B to D which is saying that 2 plus 7, right? So 2 plus 7 will give you what? 9, and A to D is 1. So what is that? Is minimum is 1. So D to destination D, to reach destination D from A, there is a distance of 1 with the next stop of D, right? So in that way, the routing table for A, the second level is created, right? Which is that one. And the routing table for the D also could be created in similar way. So in the first step, every router is going to prepare the local routing table using the knowledge about its neighbor, and in the second one, every router will take its distance vector and then process it, right? And to find out the updated routing table. So it is going to happen in a periodic manner, one after the other. So if you compare the previous routing table and the new routing table, then A to C entry was not known, but now A to C entry is having distance 5. A to C entry was not known earlier, but now A to C entry is having distance 5 through B. So this is like a two-edge path, right? So earlier single edge path was not there, but now two-edge path is there. So this is how we can say that earlier it was infinity, now it is having some path which is having two edges. The direct edge is not there, but indirect edge is there with more than one edge into consideration. So see, going in this way and identifying all the routing tables, the second level and then the third level and so on, is going to be a lengthy procedure, right? So what could be a shortcut for this? Right. So let's say at at A, we will do the computation for A. Distance vectors are available from B and D only for A, right? So what is the situation? Distance from B, what it is going to receive is, from B, it is going to receive the vector 2037, right? The previous one. And from D, it is going to receive 1, 7, 11, and 0, right? So now these two vectors are available with us from B and D. And at A, we need to find the edge weight. So what is A to B and A to D, right? So A is this for A, we need to identify what are the edge weights for A to B and A to D, right? So AB is equal to 2 and AD is equal to 1. So now we are having a vector 2, 1, which is there. Now what we do is we add this to the entire this BD vector, right? So 2, 1, then 0, 7, 3, 11, 7, 0. We add this 2, 1 to each of this and find the minimum and use it, right? So in that way, if you go ahead, then it is let's say 2, 1 is there, and for A, see, understand, for A it is what, anyway, from A to A it is 0 and A. Then for B it is 0, 7, right? So 0, 7, if I say, then if we go with 2, 1, then the 2 is the minimum the value which is possible instead of 7. So we select that one as the root, and we say B to B, right? Then 3, 11 is then added with 2, 1. So again there is a path. So 3 plus 2 is 5, and that 5 is selected, and that will be from B, right? So vector from B is the minimum one. And then 7, 0 that will be added with 2, 1. So it is anyway going to select the D part. Option is D with the value of 1, because 7 plus 2 is 9 and 0 plus 1 is 1. So minimum is 1. So from where it is there, it is from D vector. That's why the next stop is D. So in this way, we are going to calculate it for A. And at B also, what is going to happen is, at B, if you see distance vector from A, then C and D. So it is connected to 3 nodes. So right, if you look into the diagram, then we see that A, C, and D are connected to B. Right. So what is the vector available from A is 0, 2, infinity, and 1. And from C, it is the distance vector is infinity, 3, 0, and 11. And distance vector from D is 1, 7, 11, and 0. So at B, we need to find the edge weight for A, then AC, for BA, then BC, and BD, right? So from B to A, it is 2, then B to C, the edge weight is 3, and B to D, the edge weight is 7. So now, no, the similar approach would be followed. These three elements, 2, 3, 7 would be added with except except B, because B0B would be the entry inside the routing table which is newly created. So A, C, and D, for A, C, and D, no, the updation will be possible, right? So updation would be done. So shortest path, no, we are interested to find in this way, and the routing table will be created. Updated routing table will be created. So if you see here, so 0 comma infinity comma 1, if you see, it will be added with 2 comma 3 comma 7. So minimum is 2, and that it is from next top of A, so that is by 2 comma A, right? Then B is 0 comma B, 0 comma B, and then C, if you see the vector C, infinity 0 11, so that will be added with 2 comma 3 comma 7, so that is going to give you the minimum as 3, and the next top as C, right? So next is 1 11 0, which will be added with 2 3 7. So if you look into it, then what will be the minimum is 3, and from A, right? Because 1 plus 2 is 3, and from A. So the next stop is A. So in this way, this table is created for updated table is created for B, and what we get here is there are B to A and A to D. See, B to A and A to D, there was a path from B to A to D, and now earlier there was a path from B to D which was 7, and now we are having B to A to D which is 3. So B to D through A, the last line, no, that the circled one. So now now we are getting the optimal solution. So shortest path, which includes at most 2 edges, is considered here, and we are getting the better path, right, compared to 7. So this is a lengthy procedure, understand, and for n nodes, n-1 edges would be required to be could be there, right? So in our example, there are 3 edges, and so we need to go for one more round of routing table, and this is really lengthy, so we should use our intuition during the exams, otherwise it will take a lot of time during the exams, right? So we will see the overall picture, right? And see, let us look into this. From this, now we'll prepare the routing table for A. So from A0A, that's fine. So destination is A, it remains there only without changing the next stop. So it is already there. From from A to B, we are preparing the routing table for A, understand? So A to B, there is a vector, there is an edge with weight distance 2. So that is there, so 2B. Then for C, if now see, our intuition comes up here. We know that it is 111 on one side, and then there is 2 plus 3 on other side. So that is 5, and then through which router? It is through router B. So by intuition, we are preparing our table. Then there is a path from D. So A to D is 1, and the next stop is D. So A to B is used, and A to D is only used. The rest of the edges are not used. Likewise, if you prepare the routing table for B, a final routing table, so then what will be the situation is B to A, there is a path which is of length 2, and next stop is A. B to B is 0, and B to C, if you see, there is an edge which of length 3, and next stop is C. So B to D, again there is a path which is there, but see here, instead of directly going to instead of making use of the direct path, a direct edge, it is making use of the optimal possibility, which is 2 plus 1 equal to 3, right? So 3 and through router A. So understand here, the edge B to D is not used, right? So B to A is used, B to C is only used. Rest of the edges are not used, right? Likewise, if you see for C, router C, A to C to A, is it possible? So C to A is possible with the reverse path through B, right? So 3 and 2. This is only possible. Why? Because this is possible because there is no directed edges. These are all undirected edges. That's why it can follow both the directions, right? So that's why phi and B. And B to C to B. C to B is there is an edge which is of length, the distance 3. So 3 and B. Then C to C is 0, and then C to D there is a path, but instead of following this 11 distance, no, what it will do is it will follow this 3 plus 2 plus 1. So that is a better path. So that's the distance would be 6, and that next stop would be B. Likewise, no, for vector, I mean the router D, the routing table would be created. D to A is 1, then D to B is D to B is again 1 plus 2, that is 3 through A, and then D to C is 1 plus 2 plus 3, which is 6 through A, and D to D is 0. Right, so A to D is only used, understand, A to D path is only used, and rest of the two edges, if you see, observe carefully, the edge between DC and the edge between DB, these edges are not used at all. So we can, as they are never used, no, this could be removed from the system, from the network. So the question can be asked to you that what are the edges which will never be used. So the answer to this is BD and DC, right? So so the question is that is known to you now. So at D, you find 7 and 11, and you check for alternate path less than 8. So yes, there is a path which is there that we have seen. So D to A is 1, D to B instead of 7, it is 3, D to C instead of 11, it is 6. So 7 and 11, the edges will never be used. Similarly, similar things will happen at C. So for CD, CD instead of 11, there is an alternate path which is C to B to A to D, and so path 11 can be discarded, right? So in this way, the edges which are not required, no, can be very easily removed. So again, see, there is this is one thing, and then there is a problem with the distance vector routing algorithm, and that is the count to infinity problem. So what is the meaning of count to infinity is bad news spreads slow and good news spreads fast. So we'll take the example of this situation, right? So initial example, no, the first one, the good news spread fast. We'll discuss this one, the left one part. And there is a network A, B, C, and D, and the path initially from A to B was not there. Right, so A to B and 2A, we are considering 2A, right? And then because of that, there is infinity, infinity, infinity. And 1, 1 was there at the distance of 1, 1 between BC and CD was there. And now let A is connected to the network. So what is going to happen is, and with the distance of 1. So A to B, B to C, C to D, and the distance of all of them is 1. So initially it was infinity, then it will come to know that, okay, there is one path from to A and the distance is 1. So that one it will be updated in the routing table for A, in the B routing table. Right. So there still C and D is not knowing, so it will remain as infinity. And when the distance vectors will be exchanged, so then it will come to know, C will come to know that, okay, I can connect to A by 2 distances, right? So it will be updating it to 2. And still the D is not knowing till that point that, until the distance vectors are exchanged between C and D, right? So as and when the D will exchange the vector with C, it will also come to know that, no, okay, I can reach to A by 3. So this is how the good news spreads fast. But suddenly now see, this is one scenario, but the other scenario is like bad news spreads slowly. So now see, there is a path A, B, C, and D. The network is there, and then suddenly what happens is that the link between A to B is broken, right? And this is actually the bad news, right? So who will come to know about this bad news is B, right? So it will become infinity, and C and D does not know about the link down. Therefore, what will happen is it will still be 2 and 3. And now the exchange of distance vector will take place, and what will happen is C tells B that I can take you to A by 2, but it does not tell that it is through U only, that is through B only. So this is the disadvantage of DVR algorithm. Only distance is passed and not the next hop. So B will be updated to 3. B will be updated to 3 because B2C is 1 and C2A is 2. Which is wrong. Therefore, no, it is going to update it to 3 at B, right? And this is how this is updated to 3, and will continue in this way, so that the algorithm gradually will reach to the infinity. So let's say now at C, from B it is having infinity, from D it is having 3. So CB equal to 1, CD equal to 1, and after adding, minimum is 4 through D. Therefore, the root will be updated to A4D. So if you see that A4D, so in center there is 4, right, and through D. So updated routing table at C would be A4D. So what it got is 4. So now you might get a doubt, if it is already, if it already knows that the number is 2, why will it update it to greater number, right? Because the rules are, we never depend on our routing table. We depend on what we get from the universe, and we always upgrade it. So what has happened is actually infinity because of unavailability of router A. It is not infinity, right? So infinity we are reaching very slowly to infinity, and that is the bad news, spread slowly, or the count to infinity problem, right? So number of distances only to node A at practice is P, C, and D will have the entire routing table. Just to keep things simple, I have used the numbers which are distances to A, right? So otherwise, no, that it will be there. So now, depending upon, again, when this infinity, you will say that this it has reached the infinity. So depending upon the number that you have chosen to represent as infinity, it may be 32 or it may be 16. When it reaches this number, you can declare that it is infinity, right? And then you can stop. So this, what is the outcome is that the solution is, we are reaching very slowly to the for the bad news to the infinity. So if we would have send along with distance vector the next hop, then there would not be any problem. So, but as the bandwidth was low in the earlier days, right? So next hop was not sent. Also, a lot of data would be present in the distance vectors, right? A lot of distance vector data would be there. The next is distance vector needs to update to be updated periodically. That is, let's say after every 5 seconds, to find out if any link is down or the traffic is heavy or any change in the topology is there. Therefore, dynamic algorithms will keep on computing it, and even if the final answers have converged. So this algorithm will never stop as such. So dynamic algorithms will never stop. Reason is because if anything goes wrong anywhere, then we want to find out where it has gone wrong. So periodically, again, these exchanges also will happen. So it's always going to be like that. And never-ending procedures. So let's say we'll take an example to check what will be the after the exchange, what will be the value at, let's say, N3. So these are some routing tables given to you. Given to you the vectors with N2 to N3 in N3 initially as 6, and based upon that, the distance vectors are available for all the N1, N2, N3, N4, N5 routers. And then what happened is that the 6 has been changed to 2 due to some reason. So after one round of exchange, what will happen? What will be the change in N3? So that is the question. So all routing tables are going to change, understand, right? But we are interested to check only with the N3, right? So what will happen is, remember this is the question, note it down. And what will happen is you will get a vector from N2, and you will also get a vector, N3 will get a vector from N2 and N4, right? So from N2 it will get 10673, and from N4 it will get 87204, right? So from N3 to N2 and N3 to N4, what is the edge distance? That is, N3 to N2 is 2, and N3 to N4 is 2, right? So 2, 2 vector. So we'll just add this 2, 2 vector to this the vectors received from N2 and N4, right? So what we'll get is from N2 and N4, we will find out the minimum for that, right? So what change will be there? So we'll have to find out the new distance vector. So we have seen this. So 2, 2 will be added to 1, 8, right? So the minimum is 3, and that is through N2. So likewise, 2, 2 would be added to 0, 7. So it is through 2 and N2, right? And N3, by default, we are looking for N3. That's why it is 0, N3. And for N4, it will be what, 7, 0. So 7, 0 added with 2, 2. that will give you 2 with N4, right? And for N5, it is 3,4 added with 2,2. So that is 5 for through N2. So this is a new distance vector at N3, and this is the answer. So in this way, the updated routing table related questions could be there. Now the solution to this count to infinity is split horizon, right? And count to infinity not only gives the wrong values, but it also creates loops. We need to identify, we can identify the loops also, and the solution is the split horizon. So for fast convergence and no infinite loops could be there if we are having this information. So A infinity 1, let's say, is the routing table for at B level, then for it's for A, right? So at C, when you are at C routing table, it is through A to B, then A3C and so on is there. So then if the link between A to B is broken, in that case, what is going to happen is 1, 2, 3, then infinity 2, 3, then infinity will be passed. So in that way, infinity immediately would be known to the to all these stations. So that is the concept behind the split horizon. So you have to send infinity to a node on which you are depending on, and it does not mean that the entire distance vector has to be infinity. It is only for this particular entry only that we are saying that it would be the link is not there, right? So what is going to happen is, let's say at B, if you are having A, B, C, D with the 0, 1, 0, 3, 4 and A, B, A, D, and when this vector is supposed to be updated at the A routing table, so what this A routing table will do is it will say that it will see that next stop is there with A and C, so it will make it infinity, and rest of the vector, this vector, I mean infinity and infinity to A would be sent. And when it is sending to D, it will see that where is the next stop? Next stop is at the D level, right? So next stop D has a 4, and infinity would be, I mean, that will, instead of passing 4, that infinity would be passed to router D. So in that way, in this way, the routing table with infinite values will be communicated to the other routers. So this is all about distance vector routing. But before we conclude, let us see the disadvantages of distance vector routing algorithm. So there is a count to infinity problem, and then there is a convergence is very slow, and also there could be some loops inside this. So by using the solution of split horizon, we can solve the problem of count to infinity and the loops problem. But convergence rate, we are not guaranteed that it is going to improve. That's why convergence will always be slower in this case, right? So we will stop here, and in the next video I will tell you about the link state routing algorithm.